We start with a talk by Viti on geometrical correlators in 2 dimensions. So this subject will also be the subject of this afternoon's talk by Ising FK. And next week we should also have a talk by Seller on a similar subject. So Jacopo will start laying the grounds for all this. Please, let's start.
Okay, thank you very much, Sylvain. So thank you for the invitation. It's a great pleasure. So as Sylvain already explained, this talk will be an introduction to the problem of calculating geometrical quantities in two-dimensional conformal field theories. And so I will review some of the recent developments in this challenging field. And this afternoon there will be another talk by Ifei He, who will address the very latest breakthroughs that were obtained by combining with the conformal bootstrap. All right, so let me start. So what is the problem? So let's start by considering, for instance, the ferromagnetic Ising model. So in principle, in any dimension. So here is the Hamiltonian, as you all know. And so basically, if we run a Monte Carlo simulation, for instance, in 2D for simplicity, well, what you see are a snapshot of this type, where, you observe immediately, essentially, clusters of spins, right? Clusters are defined in the obvious way as connected component that contain spin variable, next neighboring spin variable, which have the same color. So here is an example here in this picture also on the right. Essentially the geometrical problem is to try to define a percolation problem such that this percolation problem, which is associated to the original lattice model, will have essentially the same critical properties. So by this, I mean more specifically the following. So consider, for instance, a spin cluster. So as I said, a cluster which contains spin of the same color. And imagine to draw an edge between two lattice sites which are within such a cluster with probability PB. So the question is, what is the value of such probability as a function of the parameter of the model, such that when the Ising model is critical, there is also a percolation phase transition. So namely, there will be an infinite cluster of such in the percolation problem. Okay, so this, of course, this question goes back to the construction already of the so-called droplet model by Fisher very long ago. So in any dimension, it turns out that it is in fact possible to construct a percolation problem that somehow includes all the critical properties of the original statistical mechanics lattice model. And this can be done, in fact, by generalizing the Ising model to its natural extension, which is the Q-color pots model. So here is the Hamiltonian of the Q-color pots model. And so how it goes, the construction of such, let's say, essentially the embedding of the lattice model inside the generalized percolation problem. Probably you know that it follows essentially from the so-called Fortuny clustering construction. So we start with this Hamiltonian. The Boltzmann weight can be rewritten as a product over edges of the lattice. So this x, y in bracket represent an edge of any of the lattice. And this product can be interpreted graphically. You can, every time you select the first factor, 1 minus PB, you leave empty the bond between x and y. While if you select the second term in the expansion, you draw an edge, you draw a bond between x and y, and you can see that this immediately implies that if you draw a bond, then the lattice variable, they have to have the same color. And the probability of such a bond, which follows from the graph expansion, is 1 minus exponential minus j, where j is the coupling here. Okay, so once you rewrite the partition function, then as a sum over the graphs which I described now, then the sum over the spin configuration is trivial because in each graph, the spin are constrained to have the same color. And so what you get is this generalized percolation problem graph as the graphs which are called FK graphs as this measure. And the presence of this factor due to the number of cluster implies that the percolation problem is in fact correlated because the bonds are not independent. And remember, the Q is the number of colors that you have available at the very beginning. So this seems is a very clever construction, in fact. The partition function becomes in this way a polynomial in Q, and in fact you can think of it as an extension, as I said at the very beginning of this talk, of the original lattice model. So in which sense the Fortuny clustering construction realized this old idea of Fisher of embedding the lattice model into a correlated percolation problem. So it does this in a very simple way, in fact, because suppose that we consider the Potts order parameter, which is this vector, Q minus one-dimensional vector. So it is a vector in the sense that it transforms irreducibly under SQ symmetry. So this vector is just defined like this. So delta S of x alpha minus 1 over Q. So it's the order parameter of the magnetic phase transition of Potts. So for instance, it's Q2, this is just the usual order parameter of Ising. So when you try to calculate the one-point function of such operator in the graph expansion, you can immediately observe that since the sum over alpha of sigma alpha is 0 by construction, then in this graph expansion, you can never have a situation where the point X is inside a cluster which is not which is not a fixed color, because otherwise the sum will produce 0. So the only graphs that survive in the expansion of the one-point function are the one which connect the point where X is inserted to the boundary, provided that the boundary has the same color alpha that is selected here. So okay, so that's graphically means that the one-point function of the order parameter is just the probability that one point's being connected to the boundary by an FK cluster, the Fortuny clustering cluster, and the thermodynamic limit, this is just the probability of having an infinite spanning cluster. So it's the order parameter of the percolative phase transition, which implies that the critical exponent of the ferromagnetic transition are in fact realized by the critical exponent of, coincides with the critical exponent of the percolation problem. So the construction for tuning clustering solves this problem of embedding a lattice model into a percolation problem and describe geometrically a ferromagnetic phase transition in terms of a percolation phase transition in any dimension. But in fact, introduce a much more interesting problem, namely the fact that the percolation problem just not reproduce the original lattice model, but hugely enlarge it. And in fact, there are much more observable that can be calculated within such a geometrical problem that they were originally. Okay, so this is easy to understand because if you mark, for instance, endpoints inside this domain, you can ask a typical question, for instance, like what is the probability they are partitioned into a certain configuration of a photon clustering cluster. So this I will call it connectivity. Is a function, of course, of the position of the points on the domain, and it can be measured in numerical simulation quite easily. And well, as I said, it's just the probability that point xi inside this domain will belong to cluster AI.
Yeah, sorry,
So,
Jacopo. Yes.
If you want to claim how that you have solved the Q-state Potts model for any Q,
Jacopo, I think there's a question.
then what this really means is that you have found all these functions. Okay?
Jacopo, do you hear us?
Sorry?
Can you hear us?
Yes.
Yeah, there's a question. Well, I have a question. So
sorry, I didn't. It's on the chat.
No, I want to ask a question.
Sorry, please.
Yeah. So why do you assume that Q is real and not complex?
Because I want to have a positive probability measure. Well, okay, if I want to interpret this as a bona fide percolation problem, but from the point of view of the extension, Q can be even complex, in fact. But okay, at this point, numerically, it's not clear what you want to simulate on the lattice.
I believe it has been shown that the probability measure exists for Q larger than 1 and real.
Yeah, this is what I said, yes. So the probability measure, otherwise it is not really defined in this way.
What is the meaning of labels A1, A2, AN? Like what are the values that they take?
It means that so A1, A2, AN are labels clusters. So it means that point xi belong to cluster AI. So in the next slide there will be more explicit. We'll see that more clearly. Okay. So basically there are two basic questions that we want to ask. The first question is how many of these functions we should calculate, and the second is can we calculate them? Okay, here I said that it's equivalent to solve the model for Q real. In fact, you can also think Q complex, but then, as I said, the interpretation in terms of correlated percolation problem becomes it doesn't hold anymore because probability measure is not real. Okay, so first of all, let me give let's try to count how many independent correlation functions we have in the problem. So as I said, these connectivities are probability to partition a set of points into clusters. So the index AI refers to the cluster to which the points belong. So for instance, in this case, if these points are marked, let's say, for instance, at x1, x2, x3, x4, x5, then this will be configuration PAA, B, C, C. Okay, notice that the only thing that matters is when these indices are different. Okay, so this is or equal. So it's somehow it's somehow a consequence of the fact that the model has some sort sense, in some sense, certain SQ symmetry. But I will be more specific. Okay, so this number of function is well known in combinatorics. It's the number of partitions set of a set of n points, and it is called Bell number. And I want to point out here some simple fact that if n is very large, this number grows super exponentially. So this already tells you that the number of correlation functions you have to calculate is larger than any one that you could calculate in a model with finite q. Okay, because roughly speaking, this number will grow like q to the n in the bona fide lattice model. Okay, so it is not even clear whether this is truly an extension. It might be, in fact, so it is not clear to me at this point in which sense you can really think this is analytic continuation of the original lattice model or the original statistical mechanics problem. Okay, so in fact, this number is not really okay. There are certain sum rules which are satisfy the probability. Of course, this is an upper bound to the number of linearly independent functions that we have to calculate. So obviously, for instance, the sum of all the probabilities is 1. So anyway, there are some rules which are satisfied by the probabilities. And in fact, a basis for the vector space of such correlation function can be defined by considering just a partition in which there are no any isolated points. Okay, so for instance, and this is explained the notation which I use here. So okay, there is only one independent one-point function which I didn't draw. There is only one linearly independent two-point function, which is probability that 2 points are in the same cluster, so PAA. There is only one linearly independent three-point function, which is labeled PAAA, and there are 4 linearly independent four-point functions. So, for instance, AABB, ABBA, ABAB, and AAAA. So this explains the notation which I was writing before, and this is true in any dimensions. Okay, so this consideration doesn't follow from it, just follows from the symmetry of the problem. In fact, it's also interesting to observe that one can formally express the connectivities, for instance, for n equal 4, in terms of spin correlation functions. So it's a linear system of equation, but this linear system of equation cannot be inverted if q is integer. In fact, one can also write a general form for the determinant in this case, and it has poles every time that q is an integer. So basically, you cannot write the p's in terms of the g's if q is integer.
Sorry, Jacopo,
yeah.
what is
Yes?
Q1 here? What is Q index 1?
Q1 means q minus 1. Yeah, sorry.
I mean,
Okay,
it only has
so-
finite number of poles. So if you take, it seems hard to believe that the determinant is going to have poles for every integer q.
No, Slava, the determinant is 0 for q equals to 0, 1, 2, 3, and 4, I believe.
Okay.
Yeah, in this case, it is 0 for q equal 1, 2, and 3. While in general, if you go up to n equal as a certain number m, then it is 0 for all the m minus 1 value. You can prove that. We So this is so in fact what it's clear is that you cannot invert this in general for integer q. Okay, so let me go on. So let me basically show the first example where these problems, let's say the problem of calculating connectivity can be understood and formulated. So this is the problem of calculating a three-point function. Okay, so the three-point connectivity of FK cluster. So basically the probability that 3 points are in the same FK cluster. So if you follow the map from the lattice model to essentially the graph expansion and in terms of the so basically the graph expansion in terms of the correlation function, the pods or the parameter, then you will find, as I said before, in general, that the three-point function, three-point connectivity is given formally by the three-point function of the pods or the parameter, but you see that there are these denominators, q minus 1, q minus 2, and this denominator is 0 for integer q equal 1 and 2. Okay. So in fact, if you want to calculate the three-point function, the three-point connectivity of FK cluster, this is, again, I repeat, is 2 in any dimension. You can see that an analytic continuation is required in Q already for the Ising model. Okay, so if you want to do so it's not possible to determine such function within the unitary theory. Okay, it requires an extension. And this is obvious because this three-point function will be 0, for instance, in any dimension for the. I think there is a question.
Yes. Yes. Do you have a simple physical picture for these poles at integer q?
Well, the physical picture is that there are quantities on the left-hand side that are not 0, a quantity on the right-hand side that are 0, and you need to have 0 with 0 in order to get something finite. So this is it's needed, because otherwise that would mean that you could invert this linear system and rewrite every let's say probabilities in terms of spin correlation function. We already know that this is impossible, because the spin correlation function, they are too few in order to invert the system. So they are needed somehow.
Excuse me, so if you want a more formal answer, there is some algebraic construction called the partition algebra that underlies all of this. And its representation theory is such that when q is a positive integer, something happens to it. So you can form non-semi-simple representations. And this is why you see all these singularities at the integers.
Okay, thank you.
Okay, thank you. Okay, so all right, so so as I said, an analytic continuation of in some sense is needed here. Okay, so from now on, let me stick to 2 dimension, because this is where, in fact, we can calculate something. All right, so in 2 dimension, basically, one postulate the existence of a conformal field theory, which at the critical point, of course, the percolation phase transition, which within this field theory, one could express this three-point function or three-point connectivity in terms of a three-point function of a certain field, scalar field, and this scalar field has conformal dimension which are fixed by the two-point function. And what is this? What are the conformal dimension? I will write in this way. So it's a scalar. So let me write it this way. So delta sigma, the conformal dimension, is twice h1/2 0 in the usual Katz parameterization for where m is the central charge given by usual formula related to q by such a relation here. Okay, so why I write h1/2 0? I write h1/2 0 to, even if in general for q integer, this will be the conformal dimension of the ordered parameter. I write like that because I want to emphasize, I think Jesper was one of the first to use this notation, in fact. I want to emphasize that the field is not degenerate. Okay, so it has no null vector when you want to basically want to try to calculate its 4-point function, at least from the point of view of Virasoro algebra representation. This representation is not any null vector. Okay, so that's difference between, despite the fact that it has the same conformal dimension of the ordered parameter. Okay, so how we can basically try to calculate this 3-point function. So this was the origin of the story, essentially. First of all, let me do a kind of trivial remark. So essentially, by conformal invariance, this 3-point function can be written as factorized as a square root of 2-point function. So the only quantity that we want to calculate as this 3-point is the OPE coefficient for phi phi phi, which I call R of Q. And what was argued essentially by analytically continuing in these indices R and S, which are in principle discrete, but you can think as continuous. The structure constant of Dotsenko Fatih F for the minimal model, it was argued that this structure constant should be given by factor square root of 2, which has some symmetry origin. But the important point is that should be given by a structure constant which in fact is remarkable, already appeared in high energy physicist context, and it will be more explicit in a moment. So this analytic continuation produces, it's analytic continuation of gamma function, essentially, produces such a function which I call C Liouville C less than 1, evaluated the value, so it's a structure constant, and it's evaluated at the value of the conformal dimension delta sigma, for which correspond to the Potts ordered parameter. Okay, the scaling dimension of the Potts ordered parameter for any Q. Okay, so what is this theory here? So let me give some remark. So it can be the best way of thinking of it is through the conformal bootstrap, and this was essentially the point made by Alyosha, Alexei Zamolodchikov, and others back in 2006. So you can start from a usual Liouville theory defined for C larger than 25. And write, essentially assume that there is a degenerate field, as usual you do, to calculate, to determine the structure constant of Liouville, and then write the conformal bootstrap equation, the crossing symmetry equation for the 4-point function of degenerate field 2, 1. After analytically continue to central charge C less than 1. Okay, you can solve this equation. There is a unique solution. This unique solution defines the structure constant. Okay, so this is the way in which you can think of it. So let me remark that already at the very beginning of its history, the structure constant was considered peculiar. In fact, the theory itself was not clear what it was. So this analytic continuation, it's not really analytic continuation of Liouville, but let's say that's Liouville theory for C less than 1. So it was considered mysterious, for instance, by Zamolodchikov himself, because it has very peculiar properties, the structure constants. For instance, it is different from zero, even if the central dimension, for instance, is zero, and the other two, they are different. Okay, so this, of course, cannot happen in any unitary theory, because it means that there exist in this theory fields with dimension zero, which are not degenerate. Okay? This was pointed out in this paper by Arlo, Maltz, and Witten in 2011 already. So essentially this theory, if it exists, necessarily is non-unitary. And it was proven to exist, in fact, recently by Sylvain Ribot and Raoul Santachiara, by making an ansatz for the spectrum and using, again, conformal bootstrap and crossing symmetry to prove that these ansatz for the spectrum lead to crossing symmetric 4-point functions. Okay, so this is what is known about this theory up to now. Okay. All right, and so it appears in this context of class test connectivity through this analytic confirmation of Dutsenko for the structure constant. Okay, so what is the evidence that this conjecture is correct? So there is numerical evidence. This was done already at the very beginning for percolation, for instance. So for Q equal 1, the structure constant of Liouville theory will give the probability that 3 points are in the same percolation cluster at the critical point in 2D. And this can be checked easily with Monte Carlo. So the value, of course, it agrees with the conjecture. And then I want also to point out that there is a beautiful interpretation of the Liouville structure constant, which was given by Yassine Clef, again Jesper, and Hubert Salaire in 2016, and they interpret this Liouville structure constant as a partition function of loops, where depending of the dimension, here delta 1, delta 2, and delta 3, the loops which separates the points Ri, for instance, from the other two, they get different fugacity. This fugacity, and one is associated to the I guess to the red loops, and 2 is associated to the blue loops, and then 3 is associated to the green loops. Okay, so calculating this partition function, then they were with transfer matrix techniques, they were able to prove, really to prove, but numerically show that this partition function was indeed given by the Liouville structure constant again. And let me also say that this loop interpretation solved geometrically the mystery of Zamolodchikov in a way. Why this 3-point function, if one internal dimension is 0, is different from 0. And the reason is that even if the blue loops, they have weight, they have fugacity, which is not modified by this conformal dimension delta 2, still the green loops and the red loops, they will have non-trivial fugacity, which leads to a non-trivial partition function. So this was this is an elegant interpretation of this mysterious value of the structure constant. Okay, so let me now move on to 4-point.
Sorry, Jacopo.
Yes.
Can I just add that maybe also I would like to mention a paper of Benoît Estienne and Yassine Clef.
Yes.
Also that they did also the non-diagonal.
Yes, exactly. This is there is also another extension due to Benoît Estienne and Yassine Clef, which sorry about that, I forgot to mention here. Okay, so all right, so let me then move to the 4-point function. This will be discussed this afternoon, in fact, more in detail. So I just want to say a few words here. So we have seen that there are four-point connectivities which are linearly independent. And once you made an answer, well, actually you don't make an answer, but you actually calculate through, again, transfer matrix techniques, the spectrum of conformal dimension entering in the conformal block decomposition of this 4-point function. You can fix the structure constant by conformal bootstrap. This will be the subject of this afternoon talk. And here I would just want to point out that if you consider, for instance, the bootstrap solution for this connectivity, so the probability that 4 points are in the same cluster, and take the limit in which x1 goes to x2, so these 2 points, they get closer to each other, then by obvious geometrical argument, this 4-point function should factorize into the product of 2 3-point function. Okay, so because all the points, they are always connected to each other, all the points, they are always in the same cluster in these configurations. So notice that there is no identity channel here. Okay, so the first, the leading singularity when x1 goes to x2 is given again by the 3-point connectivity and essentially by the square of it. So by solving the bootstrap, it was possible to verify again that this structure constant that was argued by analytically continued Dotsenko-Fatiev structure constant is indeed correct. It's a non-trivial check indeed. And this was done by, for instance, Nivesivat and Ribot, that proved that this prefactor here agrees with the Liouville structure constant up to 20, with more than 20 digits of accuracy. All right, so good. So in the following, I want to sketch simpler analytic solution of the problem determining 4-point connectivities.
Sorry, Jacopo.
Yeah.
I have a small question about that red equation. How is the overall normalization fixed? I mean, when you do the bootstrap, if you don't fuse to the identity, how do you?
Okay. This it's so let's say for when you will see the example which I will show you, I will get rid of normalization by considering ratios. So in this case, I guess the structure, I guess that, but I'm not sure. So you should ask, in fact, Sylvain probably or Jasper, that the normalization is fixed, I think, by requiring that probably the structure constant in the identity should be 1, I think, already, but I'm not sure. So in this case, there is no the identity. So, but there are, but for instance, in this case, there will be the identity. So.
Okay, thanks.
Okay. So, okay, so let me sketch now a simpler but full analytic solution, which is for this for the 4-point connectivities, which is valid when the 4 points they lie on the boundary or the domain. Okay, so this we have done quite recently, in fact. Okay, so in the case where the 4 points they lie on the boundary of the domain, so by planarity in 2D, there is a obvious simplification. So this function is 0. Okay, so there are just 3 independent, linearly independent connectivities that we have to calculate when the 4 points are on the boundary. So we are asking the probability that these points are connected by FK cluster in the first way, so horizontally, vertically, or they are all connected together. Okay? And for simplicity of the discussion, because I want to illustrate some interesting feature of the conformal field theory, which is beyond such a geometrical problem, let me focus on the Ising case, so Q equal 2, although the discussion can be done for any Q. Okay, so okay, I just mentioned that one, just for completeness, the boundary conditions that are taken here are free. So by usual scaling arguments, and if you want, again, this the Fortuny-Castle mapping, all these 3 4-point functions, they should be extracted by a 4-point function of a certain operator phi, which in this case should have the same conformal dimension of the Potts order parameter when this is inserted at the boundary. Okay, so it was shown by, in fact, argued by Cardi, that the conformal dimension in this case is the one of the field H. So it's the one of the field 1, 3 in the usual Katz parameterization. So delta sigma is H1, 3. So the field is degenerate in this case. That's the big advantage to go to the boundary case respect to the bulk case where the field is not degenerate. And for Ising, the conformal dimension is 1/2. And the spin is also 1/2, of course, because the points are on the boundary and this field is chiral. So to fix this 4-point function, what we need to do is to understand in the conformal block the composition of this 4-point function, which channel correspond to each one of those 3 functions. Okay, and this can be done by using symmetries, and also, and probably more importantly in this case, the fact that the field phi at the bound, which corresponds to the Potts spin at the boundary, is in fact degenerate. Okay, so all right, so if we consider the Ising case, so C equal 1/2. The operator product expansion of the field phi 1, 3, which is the field which I need to use, in fact, since the field is degenerate, it has null vector at level 3, has 3 channel, and this is of course very nice because it's consistent with this picture of having 3 linearly independent 4-point function. So it has 3 channels, as you can see, which I write here. So phi 1, 3 can fuse in identity, phi 1, 3 and phi 1, 5. So all the fields that lie on the first column of the cut stick. But I want to make an interesting, well, somehow a simple but interesting remark now, which is the following. So if you were in the bona fide Ising model, so the field, and you really want to calculate, you really wanted to calculate the 4-point function of the Ising spin inserted at the boundary. Okay, then you know this is of course given within the within a unitary should be calculable within a unitary boundary conformal field theory. And then in this case, it means that, well, the field phi 1, 3, which has conformal dimension 1/2, spin 1/2, should be identified with phi 2, 1, which is, in this case, just free Majorana Fermi. Okay? So what I want to point out is that if you were to calculate the bona fide correlation function of the Ising spin at the boundary, these 2 channels will disappear because of this identification. But since here we don't want to calculate really that, we want to calculate all these 3 4-point linearly independent connectivity, this identification doesn't hold, and we cannot assume it. Okay. So in fact, algebraically or more formally, we can say that these two Virasoro algebra representation, they are distinguished by the fact that in the first case, we do not, so the one which is relevant for calculating connectivities, we do not decouple the level 2 null vector of phi 1, 3 at c equal 1/2, while in the second case, we, of course, decouple it. Okay, so in the second case, we'll have a single OP channel in the fusion, and in the first case, there will be all three. Okay? So, however, this is a general fact of all this construction of geometrical quantities. When you open a new channel, which is due to the fact that you do not decouple a null vector, this new OPA channel will be singular. In fact, it will have poles. The OPA will have poles. And these poles, as it is well known, they reflect in the fact that the conformal block which is associated to this channel is also singular, and it has to be regularized, and this regularization produces logarithmic singularities. Because this has been discussed by now in many papers. Okay, so, but and this regularization is subtle, of course, and you will see this afternoon, and it's very complicated in general. Okay, so, but in my case, which is in the case where the 4 points that lies on the boundary, even if we have a singular OPA channel, the regularization of the conformal block is just prescribed by the fact that this 4-point function here solve a third-order differential equation, and the third-order differential equation is a logarithmic solution, which is already the regularized conformal block in this case. Okay, and so basically the problem now can be completely solved when the points are on the boundary, and one can write a complete analytic solution for all these three linearly independent connectivities, and calculate universal ratio out of them that can be checked with Monte Carlo and with extremely good precision. Okay, so let me now move to the last part of my talk, which, if there are no questions about this, which is basically where I want to point out some still, let's say, some open problem, something that we still have to understand in this context. Okay, so the puzzle, which is still unsolved, has to do with the characterization of the geometrical cluster of the Potts model. So these are not the FK clusters that we have seen since now, but they are really the geometrical spin clusters that are obtained by drawing bond with probability 1 between sides which have the same color. Okay, so they are really the geometrical cluster of the Potts model. So this can be typically understood in a renormalization group framework if one introduces what is called a dilute Potts model. So essentially consider a Potts model which is coupled to another Potts model. So this has been discussed, I think, also. So there was some discussion yesterday on Slack about coupled Potts model. So this is an example. So basically you see here Potts and an interaction between two other Potts variable where the values of S goes from 1 to Q, and the values of tau goes from 1 to P. Okay? So now if you perform the graphics function, the FK graphics function of this of the partition function will be associated to this Hamiltonian. Well, what you see is that the graphics function define a percolation problem where sites which belong to the same spin cluster, they can be joined together by a bond with a probability P, which is 1 minus exponential minus K. So this interaction between the two Potts model. So if K goes to infinity here, this probability is 1, and 1 describes what it will be the spin cluster, while if K is J, this probability measure is the same as the FK cluster. And the peculiarity of 2D is that both these two geometrical objects, they percolate. So there is a percolative phase transition when J, this critical, the coupling J here is the critical temperature of the Potts model, and doesn't happen in 3D. So in 3D, the spin cluster, they percolate different temperature, which is not the critical temperature of the 3D Ising model. Okay, so so the point which I want to make here is that the spin cluster and the FK cluster in general, they have, well, actually in general, they have different, even if they have the same critical point, but they percolate the same critical temperature at the Potts model, at the critical temperature as the Potts model, they have different fractal dimensions. So they are described by two different conformal field theories. So this was understood in an RG, from an RG point of view, again, quite long ago. In this sense, so suppose that we fix J equal J critical here for the Potts model, and perform a renormalization group analysis of the coupling K. Okay? So performing a renormalization group analysis of the coupling K amounts to do a renormalization group analysis of P, this probability, and so it looks for critical points of the percolation problem at the critical temperature of the Potts model. Okay, so and in fact, the phase diagram if you fix J as a function of Q for the coupling K looks like that. And so this was the discussion, basically was the outcome of this RG analysis. So, but somehow we already know that in a way. So for any values of Q, if we fix J equal J critical, there are two different fixed points for the coupling K, which is the bond probability. So one is K equal J critical, which correspond to this blue line here, and describe the percolation of the FK cluster. And then there is another fixed point, which is the normalization, which is the fixed point at which K equal infinity, namely the spin cluster, they normalize, and here is drawn by this red line. And the RG analysis suggests that these two fixed points, they merge at Q equal 4 again. So it's the same phenomena that we have seen yesterday for merging of critical and tricritical line of the Potts model. Indeed. So actually this can be made, okay, so in fact, the RG picture which I show you here suggested that critical property of a spin cluster in the Potts model that could be obtained by analytically continue quantities calculated for the FK cluster along the tricritical branch of the Potts model. Okay. And in fact, this is true if we look at the fractal dimension. So this can be done by Monte Carlo, for instance. And if you look at the fractal dimension of the spin cluster, in fact, they are really given, this is this red curve here as a function of the central charge of the Potts model. So they are really given by analytical continuation of the fractal dimension of the FK cluster, passing from the critical to the tricritical branch of the Potts model. So what is the puzzle here? The puzzle is that this analytic continuation for the fractal dimension, it fails spectacularly for the 3-point connectivity. Okay, so the 3-point connectivity of of FK cluster is what has been calculated so far and checked with extremely good precision. And certainly is a function which is analytic on the dimension, on the fractal dimension of the cluster. Okay? So you can think to analytically continue the fractal dimension of the FK cluster to the tricritical branch to get the fractal dimension of the spin cluster, and argue, of course, that the 3-point connectivity of spin cluster will be analytic continuation of the 3-point connectivity of the FK cluster. But this is actually absolutely not the case, as you can see in this picture. So this blue line corresponds to the structure, the 3-point connectivity, well, the universal ratio, in fact, which is measured by Monte Carlo as a function of Q for the FK cluster, and it obviously agree with the conjecture given by the Liouville structure constant. But when you arrive at Q = 4, well, the 3-point connectivity for spin cluster, it doesn't follow the analytic continuation of this Liouville structure constant, but it really go in a completely different way. So you can see here this red dot. So it is not clear essentially how this conformal field theory they merge at this point, or even if they can be taught as analytic continuation of one of each other at all. Okay, so this is somehow the I think a problem which is still open. So basically understanding how the spin cluster can be obtained in a conformal field theory setting, and how this conformal field theory, the one which describes the fixed point of the spin cluster and the one which describes the fixed point of the FK cluster, they actually merge at Q = 4. Okay. With this, I finish, and I hope that there will be questions, and I thank you very much for your attention.
Okay, thank you for the talk, Jacopo. Are there questions?
So hi, this is Jesper. So thanks for this very nice talk. So I guess that you compute the 3-point functions of spin clusters using these 2 coupled Potts models as you described. Is that it?
Yes.
So a long time ago with Jérôme Dubail and Hubert, we also wrote a transfer matrix that works for Q non-integer, which can identify spin clusters. So yes, it would be a natural thing to try without having 2 coupled models to try to reproduce this result by using this kind of transfer matrix.
Yes, I think so.
So that's just a remark. It would be fun to see if one could get the same result.
Yes. Yeah, somehow what I think is puzzling is this, why this, analytic continuation on this other branch seems to not be correct for the 3-point function, which I don't know why this is true.
Can I ask a question? So about this Ising cluster versus FK clusters.
Yes.
So it's yeah, I'm a bit puzzled where where this all stops, because it seems to me that I can basically come up with more and more complicated rules for forming clusters. You said, okay, I'm going to join Ising spin to the neighboring spin if they are the same color. Okay,
Yes.
and then I'm going to build something. But
well, here we can see that.
Is there like a finite set of rules which are reasonable? Because, for example, some rules which are expected to lead to some local like quantities for which you expect to be, which you seem to assume that should be true. So what makes these rules, these two rules, Ising clusters versus FK clusters, like special among gazillion other rules that one can imagine to form geometric quantities in these models?
Okay, this is I think it's a very interesting question. Okay, so so when it stopped the true answer is that I don't know. I mean, I don't have a formal answer to that. So I don't know if there exists some, well, if generalizing such percolation problem, you could basically end up in some description which, well, you could somehow find a description which is not well within usual conformal field theory, the usual conformal field theory framework. So this, I don't know.
Maybe I can say something maybe relevant. I mean,
yes.
Actually, I would hope there are a lot of different ways to generate clusters or geometrical objects, because in the CFT, in these connectivities, the spectrum of fields, when you decompose them into some channel, the spectrum is huge. I mean, it's made of a lot of primary states with cat stable indices which are not even integer, which can be fractional. So if we wanted to geometrically interpret all these fields, I mean, we would need a lot of different objects.
Yes, this is certainly true, but I'm not sure whether you can. So what is the precise relation? You cook up any percolation problem you like, and then you try to understand which conformal field theory can correspond to. This is actually well, an extremely complicated question. So
could I say something?
Yes.
In practice of a Potts model, there is actually only one rule, mainly that you have to take neighborhood spins which have the same value and connect them with some value p. When you're changing p between 0 and 1, of a particular value of p, which is equal to 1 minus exponential beta critical, you're getting the FK cluster. Okay? And you can see that there is only another value for which you're getting the spin clusters, which is a value which is p larger than the one for the FK cluster. Okay. And actually, for the Ising model, the probability p is equal to 1, and that's the only thing which exists. This has been checked a long time ago by Blöte and collaborators.
But
what does it mean it exists? Because what if you pick a different value of p? What happens?
P has to be between 0 and 1. It's just the probability that you're connecting the spins. That's it.
Yeah.
But I guess the question was if you define, some percolation where you can connect next to next.
No, this is not done. What is done is just that you're connecting the nearest neighbors. That's it.
Well, yes, for this
adding
problem,
more
yes,
than 2 neighbors has
two
never
fixed
been done.
points.
This is not true. The only thing which is done, you're just connecting the nearest neighborhood spin. That's it.
Yes.
No, but suppose that we do this, and then you come up with yet another rule that, I mean, this seems like an infinite hierarchy of problems.
So far, the only thing which has been done is connecting with P.
But this somehow is not really what we want. It's not really. I mean, the physical problem is to try to define some percolation problem where you draw a bond with a certain probability between two different sides. So
but this
Can
is
you
only-
also
of course, if
comment
you
on
allow
this?
different moves, then the theory becomes arbitrarily complicated. Yes.
Yeah, but this is going to be different. But so far, the difference between the FK cluster and the spin cluster is just the difference in the probability. But it's the same way of defining the clusters.
Yes.
You have
yes.
you have two fixed points, and that's the only thing which is known, and it has been checked carefully already. That there is no other fixed point anywhere else.
But so I don't know if this was the question was this, but somehow.
Maybe I can make a small remark. So Slava is worried, I think, that you can make arbitrarily more complicated observables by considering things as nearest neighbors, next nearest neighbors, and so on. So in percolation, if you think of a percolation cluster, it's an old problem to compute the fractal dimension of its hull. And at some point, people define something that's called the external perimeter, which means you follow the hull, but if somehow you can jump one lattice spacing over fjords so that you don't go inside the cluster. And that constructs another object that has another fractal dimension. So then you could start getting worried. Then you could say, okay, but now if I'm allowed to jump over fjords with a size of 2 lattice spacings or more, would I still keep getting different things? And actually you won't in this example. So maybe that shows you that although you can do many things, there is still some universality that hits you at some point that says you cannot do more than this.
Yeah, this has to be for sure. Now, when it stops, I don't know exactly. So,
but now that you've brought up both FK clusters and spin clusters, one obvious thing that one can do is to consider the two of them simultaneously. So you could consider probabilities that certain points belong to this and that configuration of FK cluster and simultaneously belong to this and that configuration of spin clusters. And this is another problem that has been studied in the past and that leads to yet other critical exponents.
yes, I remember that paper of yours. Yeah. I think there was a question by Andrea Cappelli.
Yes, I'm sorry for simple questions I'm asking because I'm not expert. So, but can I say that the FK geometrical model is an extension of the Potts model when Q is not integer, and then as such is not a minimal model, and then Q is integer in FK model, it reduced to the Potts model, or there is something more?
There is still something more.
Which is?
Well, which are these functions that I show you. So these connectivities, they are defined also for integer Q. And they are non-trivial. For instance, the 3-point function is already non-trivial for Q equal 2 and Q equal 1. While in the Ising case, this 3-point function is not, well, within the minimal model, that will be not calculable.
So the point is, I take this FK geometrical model. It is defined for any Q. When I take the limit Q equal to 1, I have to do some extra limit to get the Potts model.
Yeah, you have to find the correct linear combination of such correlation function that reproduces the one of the minimal theory.
So the FK model is not a minimal model even for Q integer.
Yes.
Okay, thank you.
Correct.
Yeah, Jacopo, I explain what I can. So you mentioned it's Liouville theory at c less than 1 is non-unitary, but I guess it's worse than this. No, it's logarithmic. Is it not? And in fact, all these theories you're looking at, I guess, would it be fair to say they're all logarithmic because you have no vectors that do not decouple?
Yes, it's correct. Yes. Yes.
All right. So maybe when you say it's surprising that the analytical continuation doesn't work, maybe it's even surprising, in fact, that the first case works in the first place because you completely neglected all these logarithmic aspects.
Okay, maybe, but no, I understand your point. Yeah, it's true that from the point of view of representation, that's highly non-trivial.
Yeah, I mean, like this is being understood because you don't always find logarithmic representation. For example, for the 3-point connectivity, you don't have logarithmic. So this now is well understood by the Bootstat solution. No, you have some. You can see where the logarithmic features enter in this kind of connectivities. For example,
Yes, this has been studied by us with the Coulomb-Gauss and also Sylvain recently. Also, there's a detailed study of when this logarithmic conformal blocks can arise.
Can you comment on this thing that in 3D, the two types of clusters percolate at different temperature? Then does it mean that this second type of clusters just doesn't make any sense in 3D? Or does it mean that one has to change this probability that that Marco was mentioning?
So in 3D, the spin cluster of Ising, the percolate temperature, which is smaller than the critical temperature. And this, I think, it has been even proven rigorously, probably. So, but this okay, it just it doesn't mean that they don't make sense. It just means that they are, well, this phenomena of merging for sure cannot happen in 3D of these two fixed points.
They're not critical. So if we go to the critical temperature of Ising, then these Ising clusters are not critical. No. Is this correct?
Yes.
In 3D.
But there is a percolation phase transition with critical exponent that can be defined for the spin cluster at another temperature.
Yeah, the spin cluster cannot percolate at the critical point because actually they percolate already at infinite temperature, since the percolation threshold is lower than 1/2. So you can see that they cannot percolate. But there was an old work that I have done with Dutsenko and other people in which we show that if you're taking the spin cluster at the critical point, the real critical point of the FK cluster, and you're making slice of them, then you're getting loops which actually are critical at the critical point. I just mentioned that. I don't know.
No, I remember this work, Marco, but I just was hoping that to get some extra insight in it, because if these clusters percolate at a different temperature, then yeah, what should you make of this? So does it mean that perhaps they're just a red herring and they're not interesting for physics of the Ising model, or yeah, how should we?
I don't know. It's something that we found more than 25 years ago. We still don't understand why.
Okay.
I have a comment on this. In higher dimension, the critical point is a bulk effect. Okay, so instead, this is a sort of lower dimensional effect that you can only see is irrelevant for the thermodynamics of the Ising model in 3 dimensions unless you take in the partition function, you select by boundary condition very special configuration that brings up this type of fluctuations. Okay, so it's a lower dimensional geometrical thing, and then it can only make sense if you yourself input constraints on the partition sum. That's very simple explanation. Did you get my point?
But this, for instance, will be not
I registered.
true for the FK cluster.
I cannot claim I got it, but I registered.
You don't get.
And I mean, it's a complicated things, right? Okay, so I'm happy that there are some people out there who understand this.
Okay, so you're saying my statement is simplistic. Okay, maybe
It's not simplistic. It just shows that it's a complicated problem, and it's hard to get it on the spot for people who have heard it for the first time.
In 3D, I think is nothing is really understood about these objects from field theory point of view.
Okay, are there any more questions? Well, if not, let's thank Jacopo again.
Thank you.
And we'll stop for this morning. Thank you again.